Question 20. Two resistors of resistance R1 and R2 are connecting parallel. What is the combined resistance between X and Y? So here is asking basically the total resistance of the circuit. So because they're in parallel, so the inverse of the total resistance is equal to the inverse of the sum of all the resistors in this circuit. In the circuit shown, all the resistors are identical and all the ammeters have negligible resistance. The reading A1 is 0.6 amps. What is the reading on the other ammeters? So let me start with this branch right here because the current on this ammeter is provided. So all the resistors are identical. So let me label R, or all of them. And this is the current that is flowing through this branch right here. So I'm using this Ohm's law for voltage. I label V1 because it's related to this one branch here. So the current is 0.6 and my total resistance will be 2R. Okay, so 0.6 is the current times 2R. They are in series, I add them. So the voltage is in terms of R. I cannot have a value here because I don't know how much is this resistance. Now, because this is in parallel with this, so the voltage over here is exactly 1.2 R. So let's understand the voltage first. So the voltage 1.2 in terms of R is the same one here on this branch, is the same one right here, and is the same one that is connected to those three resistors in series. So the voltage in this branch right here that we call 4, because this is A4, the voltage is the current flowing in this branch times the total resistance here, that will be the adding those three resistors. So it looks something like this, I4 times 3R. Now remember, the voltage on this branch is the same one that is on this one, 1.2 R. So V4, the voltage on this branch is 1.2 R as well. So we can cancel R with R, and now we can calculate I4 is 1.2 divided by 3. So the answer for this question is option D, 2.2. A3 is 1.2 and A4 is 0.4. Question 22. A cylindrical piece of a soft electrically conducting material has resistance R. It's rolled out so that its length is double, but its volume stays constant. What is the new resistance? To answer this question, we are using this formula for resistance. Rho L over A. However, the problem is not saying nothing about diameter or radius to calculate the area or relate the area before and after this material change shape. It's talking about the volume, so volume stays the same. The problem is saying that the material has a cylindrical shape. So that's the cylindrical shape. So the volume of a cylinder, this is the cross-sectional area, and this is the length. So the volume is area times length. But wait a minute, it says that the length of the new one is double, but the volume stays the same. Now let's take a look in this formula. If the volume is the same and the length double, so the area is reduced by half to keep the volume the same. So like this. So the area is reduced by half and the length is double. So that way, the volume stays the same as original. So now we can use this analogy to our formula for resistance. Now the resistance after the change in shape, so rho is the same. Now the length is double and the area is reduced by half. Solving this is, we have rho 2L over A. Now this denominator of this fraction is going to be flipped to the numerator, and this is 4 rho L over A. Now this is exactly the value of R. So the new resistance, the new one, the new resistance will be 4 times the old one. So this is the answer. Question 23. The IV characteristics of two electrical components, P and Q, are shown below. Which statement is correct? So now I have to look one by one to eliminate or consider as possible answer. Option A, P is a resistor? Yes, because it's a straight line on an IV graph, because the value is constant, is a fixed resistor. Q is a filament lamp. No, a filament lamp will have a IV graph like this, not the opposite. This is IV for a filament lamp. Option B, the resistance of Q increases as the current in it increases. To determine if the resistance of Q increases, we need to draw a tangent line. So a tangent line is a line that does not cross. Let's get a few points here. 1, there's another one here, 2, and another one here, 3. So let's see what happened to those tangent line as the current increases. So this tangent line is getting steeper. So steeper the line indicates the resistance is getting lower. Another way to see this is the current. So current and resistance, they are inversely proportional. So which means that if the current is increasing here, means that the resistance is decreasing. So now we're getting steeper, so we have more current, which means the resistance is decreasing, not increasing. So this is no as well. So the resistance of Q is decreasing, not increasing. Let's take a look at C. At 1.9 amps, the resistance of Q is approximately half that of P. So here is where the graph of Q and the graph of P, they cross. So which means at this point, they have the same current. Let's assume this is 1.9, like the option is talking about. So here at this current, the resistance of Q and P are the same, which makes this option incorrect. The last option, and probably the correct one, but let's check. At 0.5 amps, the power dissipated in Q is double than in P. So let's take a look at 0.5 amps. This is where cross P with 2 volts, and this is where crosses Q at 4 volts. So the power dissipated P at P, for the P graph is 1 watts, and for the Q, for this one, 0.5 times 4 is 2 watts. So this is correct. So the power dissipate at Q is double as than P. So yes, that's the correct one. 24. Which electrical quantity would be the result of a calculation in which energy is divided by charge? Now here we have all the formulas for current, potential difference, power, and resistance in terms of its own definition, not in terms of Ohm's law. So here we have for current is the rate of flowing charge, or charge over time. The voltage, which is potential difference, is the energy over charge. The power is also a rate, is the rate of energy dissipated or energy provided, which is energy over time. So, and power and current both are considered as rate because they are over time. And resistance is resistivity times the length of a wire divided by the wire cross-sectional area. So to answer this question, each of the option is a result of the calculation at which energy is divided by charge, so that will be potential difference. Question 25. A thermistor and another component are connected to a constant voltage supply. A voltmeter is connected across one of the components. The temperature of the thermistor is then reduced but no other changes are made. In which circuit will the voltmeter reading increase? Thermistors are resistors that change its value with the temperature. So when it's cold, the resistance of a thermistor is high. So the problem states that the temperature of the thermistor is reduced, so which means that its resistance increased. In all 4 circuits, the thermistor is connected. Circuit A, we have a light-dependent resistor connected in parallel to a thermistor, now with a high resistance. In this case, there will be no change in voltage because those two, they are in parallel and in parallel with the voltage supply. So there is no change. In option B, now we have the thermistor and the light-dependent resistor connecting series. So which means this power supply is going to share between both. So because now the thermistor has a higher resistance, so the voltmeter is going to read higher value than this one. So this is not correct because this V is going to read a lower value. Circuit for option C. Now we have a fixed resistor connected to a thermistor. They are in series. Okay, so what is happening is the voltage is going to share the energy between those two components. So no changes here. And this one here, the resistance has increased, so the voltage here should be higher. So in this case, the reading increase. So before make our final selection, let's take a look on option D. On option D, the thermistor is here, and this you have a variable resistor with no change. So since this one here is very similar to this, because the voltmeter is not connected to the thermistor, it's connected to the second component. So since the resistance is higher, so the value of the voltage drop on this will be way higher than this. So this here is going to read a lower V. So the best option for this problem is option C. Question 26. The diagram shows a potentiometer and a fixed resistor. This is the potentiometer, this is the fixed resistor connected across a 12 volts battery of negligible internal resistance. The fixed resistor and the potentiometer each have resistance 20 ohms. The circuit is designed to provide a variable output voltage. What is the range of this output voltage? So this resistor is variable. So it's going from 0 to 20 ohms. So now we are going to calculate the output voltage based on those extreme values, 0 and 20. So let's go for 0. So when the potentiometer, the resistance is 0 here. So it will be V in, which is 12, times the value here, which is 0, over 20 plus 0. So, of course, for this case, it will be 0 volts. Now, when the potentiometer has the maximum value, which is 20, so now it will be V in, which is 12, input voltage, V in, that's what I'm talking about, times the resistance, which is 20, over and then you have to add both, they are in series, 40 ohms. So now when you do the math, this V out will be 6 volts, which is answer A. Question 27. A battery has an EMF of 3 volts and internal resistance of 2 ohms. The battery is connected to a load of 4 ohms. What are the terminal potential difference V and output power P? So what it's asking here is terminal potential difference. So it's asking for the PD, and it didn't specify where, but by now you should know if you have a EMF and then which is from the battery, your PD will be on the resistor connected to the battery. So the PD is asking is on this one. So you need to find the voltage on this, the voltage across this resistor right here. So we can use potential divider formula, so we don't have to calculate the current. So let's call this V out, just to keep like consistency with the formula. So V out is V in times the resistance, the resistor that we have, you want to calculate, in this case 4, over the sum of all the resistors. They are in series in the circuit, in this case 2 connected to 4, so that will be 6. So your V out here is, since V in is 3, so 3 times 4 divided by 6, we have a V out of 2 volts. In terms of the output power, so we didn't calculate the current, we have the voltage, so why not use this formula, is V squared over R. So our V is 2 squared, our R is 4, so the output power will be 1 watts, which is option C. So this problem is pretty long, but it's pretty simple, so stay with me. In the circuit below, P is a potentiometer of total resistance 10 ohms. What that means is it's going to range from 0 ohms to 10 ohms. And Q is a fixed resistor of resistance of 10 ohms. The battery has an EMF of 4 and negligible internal resistance. The voltmeter has a very high resistance. This is extra information because all voltmeters, they have to be connected in parallel with the circuit, and they have to have the high resistance, so no current flow through here. So there is no any modification in the circuit. Just was a parenthesis here. The slider of the potentiometer is moved from X to Y, and the graph of voltmeter reading, V, is plotted against the slider position. See? What it does is, it's kind of lab experiment where you are going to use a voltmeter and you are going to slide different slots for the potentiometer, and then you are going to read, and you are going to use this data and present in a graph form. So each graph will be produced by this story. First, let's look the options to kind of define a plan on how to do this. So all the options, we see something in common. Those numbers 2 and 4. So where this come from? So now let's take a look where they got this 2, where they got this 4. So we could use the output voltage formula and the extreme values of these potentiometer and calculate those two values for when it's 0 and when it's 10. So let's see what we get. So we have this table here that we are going to use the output voltage formula to calculate for when P is 0 and when P is 10. We are working only with P because Q is a fixed value resistor. So this is the one that is actually changing its value. So we are using just the extreme ones. Okay, so when P is 0, and because the voltmeter is right here, mainly on this fixed resistor, so we are using this 10 right here. So Vn is 4 times the value of this resistor over the sum of the resistors they are in series. So in this case, now is 0 and this is 10. So it's 4 volts. Now when P is 10, so same thing. The voltage is on this section is Vn, which is 4 times 10, didn't change, over the sum of the resistors in series. Now is 10 times 10 is 20. So now the Vmax is 2 volts. So based on our result, we have as a minimum voltage 4 and maximum voltage 2. So we know that A and D, they are eliminated. So we have B and C to look at. Which one are you gonna pick? The problem states the slider is moving from X to Y, like this, X to Y, from 0 to 10. So our V minimum is 4, so we start right here. And for the maximum value will be 2. So the option B is the correct one. Question 29. The resistance of a metal cube is measured metal cube. So all three sizes are equal. Is measured by placing between two parallel plates. The cube has volume V and is made of a material with resistivity ρ. The connections to the cube have negligible resistance. Which expression gives the electrical resistance of the metal cube between X and Y? Okay, since this is a cube, so all the sizes are equal. So the L, L, and L. So let's count relate to the formula for resistance. Okay, so rho L and the area is, okay, so the resistance is resistivity times L, and the area is, the cross-sectional area is L times L. And then we can cancel this out. So now the resistance is just rho over L. Okay, it seems that you need to do some more work to get one of the options here, because this V is the volume. So we need to find a way to integrate what we have with the volume of this cube. So the volume of this cube will be the cube, the side cube, which means that my L can be rewritten V1 over 3. Great, so now let's rewrite all this. Is V 1/3. And this is the final answer. Question 30. A researcher has 2 pieces of copper of the same volume. All of the first piece is made of into a cylindrical resistor P of length X. All of the second piece is made into uniform wires, each of the same length x, which he connects between two bars of negligible resistance to form a resistor Q. How do the electrical resistance of P and Q compare? Okay, the problem provides two very important information here. One is the volume of P and Q are the same, and the length of P and Q are also the same. So in terms of volume of a cylinder is the length times the cross-sectional area. So the volume, and the same one here, however, is the way of all those little lines when combined together because they have the same volume. So all these, when you add all those small wires, they will have the same volume and they will have the same area. So when we look at the formula for the resistance, the material is the same, the length is the same, and the cross-sectional area is going to end up the same because the volume of this is equal to this. So we can conclude that P and Q, they have the same resistance.